Alright, my friend, today we have a tricky one. So I really hope you are fresh, you've taken your coffee, and we are ready to go. We have to create a function that displays the memory area on screen. The display of this memory should be split into 3 columns, separated by a space. So we have to write the hexadecimal address of the first line's first character followed by a colon, the content in hexadecimal with a space, each 2 characters, and should be padded with spaces if needed. The content in printable chars. Then we have some constraints, namely if a character is not printable, it will be replaced by a dot, namely if a char is in the range 131 or is equal to 127. By now you should know this stuff. If you don't understand this point, just check my previous video. Each line should handle 16 chars. If size equals 0, nothing should be displayed. This is the output that we should get. Alright, so we have the address in hexadecimal, then a colon, then we have indeed the content in hexadecimal of the string, and then we have the string itself with dots where we have non-printable chars. Here's a prototype, a function that returns a void pointer. We have to understand this concept in this video, and takes as an input a void pointer called address and an unsigned int size. This function should return the address, okay? So this is probably the first real exercise, real project, real program that we stumble upon in our journey. All right, no problem. Let's dive into the code. So as you can see here, we have all the program and it's kind of longish. So I think it doesn't make any sense to try to understand the whole program in its totality. Let me explain better. Basically, this program is divided into logical chunks. As we previously read, we have to write the hexadecimal address of the first char, then the content in hexadecimal of this string, and then the content of the printable chars. Okay, so we can divide this bigger project, bigger program into 3 sub-chunks, 3 modules, so we can really understand what is going on for every part of this project. This way of thinking, this way of approaching problems is called the divide and conquer approach, which is a very, very important approach of solving problems. Basically, we take a big problem and we divide into chunks, manageable chunks. That's exactly what we're gonna try to do with this program. The first problem I'm gonna tackle is the hexadecimal address of the first char. So I'm gonna show you 3 different programs. Each one of the program is gonna solve one specific problem, and then at the end we're gonna unite all of them. Namely, this is the final program with all the bits, with all the chunks, with all the modules united together, okay? So now I'm gonna launch this program just to prove you that it works. I'm gonna compile the code and then just run. Here it comes. As you can see, we have here the address in hexadecimal with a colon. Then we have the content of the string in hexadecimal with 1 space interleaved every couple. And then we have the string itself with some points where we have non-printable chars. For reference, these are exactly the strings of the exercise, okay? All right, let's start from here, from the hexadecimal address of the first line's first char. So as you can see here, I have a program that is going to write an address in hexadecimal of a random string. In this case, I have the string hello, as you can see here, the array string hello. All right, let's try to understand what is happening inside this code, okay? Which is not particularly long and difficult, I would say. We start from here, from this typedef unsigned char byte t. What the heck is this command? By now, we are going to forget this line because I'm going to explain to you exactly where we're going to need it, okay? So it will make more sense. By now it's going to be just a dry theory, which is useless. Then here I have all my prototypes. These are just to use the main function at the very top. The implementation is going to be beneath the main. You perfectly know prototypes at this point, I guess. The only thing is that, look at that. When I have prototypes, I don't have to insert the name of the variable. I just need the data type. In this case, byte t is the data type that I've created. I will explain later, I repeat. So we start from the main function, the Tinder main function. Here I declare an array string that I initialize with hello, okay? Very easy. So I have in my stack an array with these chars. Then I call a printf. This is just for me to print the address of str, namely the address of the first char, because the name of the array is the address of the first char, okay? By now, you should know all the array decaying into the pointer to the first char. If not, check my video. And then I just call my function print address x. You can understand that this is a function that is going to print the address in hexadecimal, exactly like this printf, right? I give the name of my array as an input, and then I do this typecast. So first important lesson from this exercise. What is a void pointer? You see, in this slide, you have a clear representation of a void pointer. Basically, it is a normal pointer made up of 8 bytes with a state that is representing an address, okay? Void is a strange type. We can consider void as a type, but not as a data type. It doesn't make any sense to have a void data type, right? Indeed, you cannot create a variable of type void. So its full utility is that of a placeholder. Let me explain better. For pointers, when we don't know the object pointed by the pointer itself, we say, hey, compiler, I don't know which is the object pointed by this specific pointer. I will tell you later what object is pointed, but by now, just save it as a void pointer, namely a pointer without a type. So when you declare a void pointer, or you make a cast to a void pointer like I just did, you're going to say to the compiler, hey, compiler, by now just take this pointer as an address that has no type, okay? I will tell you later how to use this address. By now, as long as you're aware of, this is a void pointer. This is a pointer without a specific type. So void indeed can be misleading. When you see void, think always without a type. Void means without a type, okay? So you cannot dereference a pointer without a type, because the type is telling exactly to the compiler how to dereference that specific pointer. Let me explain better, because I understand this can be a tricky part. Every time you make a cast, you're assigning a role to a pointer. In this case, for example, I have a void pointer. As I just told you, a pointer that is not pointing to any specific data type. At a certain point, I can say, hey, I want this pointer to point, for example, to an integer, okay? So I'm casting that void pointer to a pointer to an integer. What does it mean? Well, it means that the pointer, which previously was without a type, now is pointing to an integer. Namely, is pointing to 4 bytes, right? When you are gonna dereference the pointer, now that has been casted, you're gonna get an integer. Because the compiler now knows that, oh, okay, now this is a pointer to an integer. It means that when you're gonna dereference this pointer, I will read an integer, okay? The operation of casting is very easy, is assigning a role. Like in real world, when we have casting for actors, we assign roles to the actors, right? You can recall with this stupid tip. When we do a typecast, we're assigning a role to a pointer that in that moment, like in our example, is a void pointer, namely a pointer without any role, right? I can also cast the void pointer to a char. I make just char pdr. So I assign the role to this pointer as a pointer to char. The compiler, from now on, when we're gonna dereference this pointer, is gonna give us back a char, because we told him to do so, right? That's basically the idea of void pointer. We use them just as a placeholder when we have addresses without a specific type. So we, as a programmer, we have to decide which role these pointers will have to play in our program, okay? With what? With the typecasting operation. I think it's easy, right? Take your time to understand this concept, it's important. So coming back to our code, I just call my function print address in hexadecimal, and I give my address, str, as a void pointer, okay? So simply with this sentence, with this expression, I'm gonna say, okay, take these pointers to string and convert it to a pointer to void, namely an address, a generic address. Compiler, I will tell you later exactly the role of this address, okay? By now, you just take an address. That's basically it. In this specific example that I will show you is not even important, but in the overall program, in the overall exercise, we use void pointers. So for consistency, I want to use a void pointer even here. You have to understand this concept. So from here, we jump to the print address in hexadecimal, okay? This function takes as an input, as you saw before, a void pointer, a generic address, okay? Then here I do something tricky. I create a pointer to a byte. Now it's time to go back to the first line of the program. You see here, I have a typedef, which stands for type definition. Namely, this is a command to create your own type. Then I have unsigned char, which is an unsigned char, namely 1 byte, which is not signed, right? Because when you have a normal char, you have positive and negative values. But when you have unsigned char, you have 1 byte, namely values that can range from 0 to 255, right? 8 bits. And then I call this data type byte t for type, byte type. What is this line? What is for? Well, you perfectly know by now that I can stock inside my RAM 2 families of data type. I have integer data type and real. There is a qualitatively difference between the 2 data type. For the real numbers, namely floats and doubles, you have a specific encoding. So the difference is in the way this data is stocked in memory, and of course the size that this data is taking up. For example, when we have a char, we have 1 byte. When we have a long, we have 8 bytes allocated in memory. As well as when we have a float, we allocate 4 bytes. For a double, we allocate 8 bytes, right? Generally speaking. As I told you before, there is a qualitatively difference between these 2 family of data. For the integer data type, we have a normal encoding, while for the floats, we have a special encoding. Namely, we have the sign bit, and then we have 8 bits, for example, for our float, for the exponents. So we have a tricky encoding for our floating point numbers. Now, when I want to create my byte data type, how can I do that? I cannot use floats. First of all, because I don't have a data type of family float, which is only 1 byte long. Right? I have floats and doubles, which are 4 and 8 bytes. Furthermore, this data type has an encoding which is specific to its data type, so it's useless for my purpose now. So I have to use an integer if I want a data type byte. What can I use for a byte? I can use a char. A char is indeed 1 byte. There is only one little problem, that a char is a signed value. So it's gonna stock even values which are negatives, which is not natural for a byte, namely 8 bits. So what can I do to have a byte? Well, I can have an unsigned char. An unsigned char is exactly 1 byte. Maybe by now you don't understand why I need this data type, but you will very soon. So by now you understand that an unsigned char is essentially 1 byte in memory. The physical byte is an unsigned char. All right, let's keep with the code. So here, with this typedef unsigned char byte t, I'm creating a data type byte, which is essentially 1 byte in memory. Perfect. So here we have the point in which everything is gonna come together. I declare here a data type pointer to a byte. Okay, so I have my byte t, aka unsigned char, a pointer of course. The name of this pointer is pointer to byte. I've created a pointer to 1 byte in memory. Okay, easy. Then to this pointer to a byte, what I'm gonna assign? I'm gonna assign, look very carefully now, the address of S. Okay, namely, I am gonna assign to this pointer the address of a pointer. You see, S is just the string, namely is the pointer to this H. So here I have a pointer to a pointer, the address of a pointer, namely a pointer to a pointer. What am I doing here? I get the address of this pointer, I convert it to a pointer to a byte, namely the object I just created, and assign to this pointer to byte. So you understand here what I'm doing. I want the address of my pointer, okay? And I'm gonna stock inside a pointer that is able to dereference byte by byte, you see? When I'm gonna dereference this pointer to byte, I'm gonna access 1 byte of the pointer pointing to the string, you see? Just understand very well this passage, which is crucial for the understanding of the overall program. Basically, I take the pointer to the pointer, okay? And I say to the compiler, hey, this is gonna be a pointer to a byte, namely a pointer to an unsigned char. When I'm gonna dereference this pointer, please dereference byte per byte as an unsigned char, aka a byte, okay? In this fashion, I'm able to read byte by byte the values of the pointer. Doing that, I can write in hexadecimal the value of every byte. Let's go on with the code so you can understand better what is going on. But these two lines are very, very important. Make sure that you understand what is going on, stop the video, we're able to go on. Then I have a for loop. You cannot use for loop, but it's very easy to switch from for to while. So this is just for comprehension of the overall code. I say for int equals 7, int measure equals 0, minus minus I. So you see, I start from 7, and now you will understand very well why. I printf the bytes. This printf is just for formatting reason to let you understand better the output. And then I call my function print byte x1 because I have two functions, you will see. And then what do? I dereference the pointer byte plus I. I initially, you see, is 7. So I dereference pointer byte plus 7, which is the most significant byte of my address. Why in position 7? Well, because we have a little endian machine. When we have a little endian machine, it simply means that the least significant byte is in the least significant position. You can recall like the little byte is in the little position, okay? Now, in this case, I have to print, first of all, the most significant byte. That's why I start from 7. 7 because a pointer is made up of 8 bytes, as you know. So we have from 0 to 7 positions in my pointer. I say, hey, first of all, print the byte which is in position 7, okay? So I dereference this pointer. I recall to you is a pointer to a byte. So when I'm gonna dereference this pointer, the compiler knows that I have to dereference it as what? As an unsigned char. So the object that will obtain by this expression is an unsigned char, exactly what I want in my function print byte in hexadecimal. Now we jump in the function itself. I have here print byte in hexadecimal 1 and print byte in hexadecimal 2. They are exactly the same functions implemented in two different ways, okay? I will explain immediately. First of all, we have the print byte hexadecimal 1. This takes as an input a byte, namely an unsigned char called byte, okay? So here I have one chunk, I have 1 byte. I have to print the hexadecimal of this object, right? How do I do that? Well, let's say if byte divided by 16 is minor 10, what do? Here I use printf, but just for understanding. In the overall program, I use the write function. I say print the char 48 plus byte divided 16. So I'm gonna get 48 plus a value ranging from 0 to 9, because I have this constraint here, right? So what is 48 plus a value ranging from 0 to 9? My friend, it simply is the range of integer chars, right? From 48 to 57. On the contrary, if you have a value which is major than 9, you're gonna add 87 plus this value. So it's gonna be 87 plus 10, for example, 87 plus 11, 87 plus 12. What is this value, my friend? Well, I use 87 because I need an offset from the first lowercase char 97 of 10, right? You understand this point? Here at this elf, I'm sure that I have a value which is 10 or more, right? So here I need 87 plus maybe here I have 10, so it's gonna be a lowercase, you see? 97a, 98b, 99c, 100d, and so forth. So this is just a way to print in hexadecimal, you see. This is the block that is gonna handle the most significant 4 bits. And these the lines of code that are gonna handle the 4 least significant bits. Here, as you can see, I use the divisor, and here I use the modulo. Now, I understand this can be tricky, so I'm gonna explain you how it works mathematically. So, my friend, here you have 1 byte. 1 byte in this case is the value 214. Of course, this is an unsigned char. Otherwise, it would be the value minus 42. And not 214. So I have this byte. The value in this case is, I repeat, is 214. The binary configuration is 11010110, and the hexadecimal is D6. By now you should know that the hexadecimal notation is very handy for chunks of 4 bits, namely a nibble. They are called a nibble. I can really see 4 bits chunk by chunk. So I can read this number in decimal like 214, in binary with this fancy binary configuration, on in hexadecimal as D6. Why D6? Well, you see, the 4 most significant bits are the number 13, which in hexadecimal is D, right? And the 4 least significant bits are 6, namely 6 in hexadecimal. So D6. How can I get the 4 most significant bits of this byte? Well, I can do division. I can do division by 16. If I take indeed 214 and I divide this number for 16, I get the number 13, indeed, the letter D. If I do modulo 16 of this number, I get 6. Try by yourself. So you see that with division, I get the 4 most significant bits, and with modulo, I get the 4 least significant bits. It's very handy. Why it works the way it works? Well, it's very easy. Now I'm gonna explain you with base 10, so you can have a very easy understanding. When I make division by 10 of 92, around the number, what do I take? Well, I take the number 9 and I throw in the bin the 2, right? And the 2 divided by 10 is gonna be 9, because I have truncation, of course. If I do 92 modulo 10, and I repeat, this is a decimal number, modulo 10, I take 2, right? Easy. You understand very well. So when I make division by 10, it's like taking the most significant value. It's like cutting the least significant value. The same, but inverse, also for the modulo operation. When I do modulo 10, I just take the 2 and I throw in the bin the 9, okay? Let's make this operation with base 16 this time. I have the number D6 that you saw before, it's just the number 214 in decimal. If I say D6 divided by 16, I get 13, namely D, I get D in hexadecimal. And if I make this number, D6, aka 214 modulo 16, I get 6. Of course, this trick holds only because we have 2 values in hexadecimal, right? We have FD, but if we had 3 values, this trick wouldn't this mathematical trick wouldn't work anymore, because we, like for example, if we have 792 in decimal divided by 10, we get 79 and not 9. The modulo still works because we get the last value. You get the point? In base 16, if we have the value FD6 divided by 16, I get 253, which is FD in hexadecimal. But this won't work. So I hope you get the point here. When I make byte divided by 16, a byte is a value ranging from 0 to 255. 255 is FF in hexadecimal. When I say byte divided by 16, I'm talking about the 4 most significant bits. And I say, hey, these 4 significant bits are minor to 10. Namely, is this an hexadecimal integer char? Well, if this is the case, just print the char, the integer char, okay? Namely, with 48 plus byte divided 16. It's going to be a value ranging from 0 to 9, okay? Otherwise, you have to print an alphabetical char starting from 97. So here I have a value from 10 to 15. I'm going to say 87 plus 10, for example, and it's going to be the char A. Or byte plus, I don't know, 11 is going to be the char B. So these 4 lines are handling the 4 most significant bits of the byte, and these are handling the 4 least significant bits of the byte. I hope this is clear by now. So you see why I need a byte type, namely an unsigned char type, because here I'm using the value of the byte. I'm using byte divided by 16. If I have a normal char, namely an object that can also represent negative values, this operation won't be valid, okay? All right, this is the first method of printing the hexadecimal of a byte. Now I'm gonna show you the other one, which is the one I like more. Here, as usual, I have my print byte x, this time 2. This object is taking an unsigned char, aka byte type, with the name of the object byte, namely my 8 bits, okay? I declare 2 integer, I call upper bits and lower bits, just to be extremely pedantic, and I say, okay, the 4 upper bits are the byte and logic with this binary, okay? And then I shift this value by 4. What the heck am I doing here? Don't worry, it's super simple, even this operation. You see here, same idea. I have my byte that has a value, the value 214, D6 in hexadecimal. Now what do? I want to isolate the D, the hexadecimal D, namely the most significant 4 bits, because I want to write in the standard output. What can I do here? Well, I can do something really tricky. I'm gonna do an AND logic. This is a bitwise operation. I'm gonna AND the first byte with another byte, which is 1111000. This is called a mask. Maybe I'm gonna link you some videos so you can understand this point, but it's very easy. And AND logic, this masking is gonna give me back most significant bits, because the bitwise AND logic is gonna give me back 1 only if the 2 bits are true, namely only if the 2 bits are on. This kind of masking is gonna zero all the least significant bits. I think it's super easy. All right, now I have 1 byte that contains only the 4 most significant bits. Perfect. But there is a problem. I still have significant bits on the right, all the zeros on the right of the most significant bits. These are significant. I bet you want a salary that has many zeros on the right? So I have to do something at this point. I have to perform a shift operation. A shift operation is very simple if you see like that, if you have a visual understanding. Basically, it's like, hey, can you move all the bits 4 position on the right? That's basically what happens. So shift 4 is going to shift the bit. It's a very low-level operation that has a significance. And now you will understand what does it mean to shift 4 position 1 some bits. By now you perfectly know division. When I have one number, like in this case 1492 divided by 1000, it's like removing 3 digits and I take only the one, right? If a division is for 100, I remove only 2 digits, and by 10 I remove only 1 digit. It's very easy for you. You can perceive the division like a scissor cutting the value. Now let's make the division with a binary number. Here I have the number 9, right? 1001, it's 9, divided by 8, namely 1000 in binary. This division is like removing the 3 values, right? It's like removing 001, because 9 divided by 8 is 1, and this is exactly. Then I have 9 divided by 4, is like removing 2 digits at the bottom, so I get the value 2. 9 divided by 4 is 2, 10 in binary. If I say 9 divided by 2 in binary, I get the value 4, exactly. I get 4 with the loss of 1. So you see, if I divide a binary number by 8, by 4, and by 2, it's like removing 3, 2, and 1 digit. It's like cutting them. Exactly like in base 10. If I divide it by 1000, I remove 3 digits. If I divide by 100, I remove 2 digits. And if I divide by 10, I remove 1 digit. Basically, it's very easy. In base 10, you have powers of 10, while in base 2, you have powers of 2. You have 2, 4, and 8. So look carefully now. You have the binary value 9, 1001. Divided by 8 is like removing 3 digits, right? Because 8 is 2 to the 3, so we have to remove 3 digits. We remain only with the 1. Indeed, 9 divided by 8 is 1. Here I do something different. I push in the bin 3 digits, and I stay with the 1. You see? When I do shift 3 position, it's like making the division of the number by 8. Dividing a number by 8 or make a shift of 3 position is exactly the same at the binary level. As well, if I make a shift left of 3 position, it's like multiplying by 8. Just check a number. You have the binary configuration of 72, which is exactly 9 per 8. So with the shift operation, I can multiply or divide numbers by powers of 2 at the binary level. To make it super clear, if I had the opportunity to perform the shift for decimal number, which is not the case in computers, I would say, okay, 1492 divided by 1000 is gonna result in 1, with the truncation of 492, which is the same as pushing into the bin for 9 and 2, pushing 3 position the number. The same logic applies for multiplication. So shifting by 3 position is like dividing by 1000. If in decimal number, that's the same logic, guys. That's exactly the same logic, only we are working with powers of 2 in computer. Okay? So in our code here, what's happening? I make a bitwise operation here. I take my byte and I take the 4 most significant bits. And then I do a shift 4. You now totally understand that this is like making the division by 16. Here if I say shift 4 or if I say divided 16 is exactly the same operation. Basically, I'm going to shift these 4 bits here. Okay, now what do I have? Well, I have the 4 upper bits, which are a value ranging from 0 to 15. I say, these 4 upper bits are minor than 10. If yes, just print the integer char, okay? Otherwise, you print the lowercase alphabetical char. I use 87 for the same reason of before, because I need an offset of 10. 97 is the first lowercase char. Perfect. Then what do? The same logic as before. I need this time the 4 lowercase bits. This time I don't need the shift operation. I just take the byte, I make an endwise operation with this mask. You see, I'm gonna take only the least significant bits with this mask. This time the zeros, which are on the left of the number, are not significant. That's why I don't need the shift operation like here. Then I say, okay, these bits are minor than 10 and all the jazz as before. You understand very well. This is the function to print the hexadecimal of every byte, okay? Here I don't necessarily use the byte type, namely unsigned char type, because I'm not using the value of the byte, I'm using the bits. Namely, I'm not using a division on the byte itself. I'm taking chunks of 4 bits. But anyway, for consistency, I used byte type. That's it, my friend. These are the 2 functions that are able to print in hexadecimal 1 byte. So what's happening here? For 7 times, I'm gonna dereference a specific byte of my address, giving as an input to the function print byte. So every time I decrease by 1, namely I decrease by 1 the byte I want to dereference, reaching the least significant byte, which is the one at position 0. That's why here I have I major equals 0. And that's it. This is a program that is able to print an address in hexadecimal. So let's go back to the top. I have the creation of my data type, a byte type, then my prototypes, so I can have my main at the top, and then I have my main. My string, printf, is going to print the address with the printf function, and then my print address in hexadecimal, which is essentially specular to this. Let's see how it works. Okay, I'm gonna run this code, and you see here I have the address of the string, and then in a very cozy way I've written the address in this fashion. So I have byte by byte in hexadecimal written the address. You see I have 0000, then I have 7f, which is the byte 5, then I have fa, which is the byte 4, e6, which is the byte 3, b6, byte 2, 29, and ca, easy vanilla, right? Okay, now you understand how to print an address. Let's go on. I want to just to show you that both the function work exactly like the same. This time I'm gonna use the function to, which is the one working bitwise. See, that's exactly the same. That's exactly the same, okay? So it boils down to your preference. I personally prefer the bitwise, but that's the same. Okay, we have solved this problem, the hexadecimal address of the first line. Then we have the content in hexadecimal with a space. It's very similar to the problem we just solved, right? So second point in my divide and conquer approach, the content in hexadecimal with the space, as I just told you. As well as before, I have my typedef, namely unsigned char byte t. Then, as you saw before, my function prints byte hexadecimal. You saw before, that's the same thing as before. I have one implementation, and here I have the bitwise implementation, the one I like more. But anyway, so this big boy function, now you understand very well. This is a black box that takes 1 byte, namely an unsigned char, and it's gonna print in hexadecimal the content of this byte. So we can only focus on our main and my print string in hexadecimal. Here I have my string. This time I use a char star string, okay? And I have hello world, how are you? As a content of this string. I call then my function print str in hexadecimal. So let's jump here. This function takes, of course, a pointer to a string. Here I declare an iterator I that I initialize with 0. Then I say while at str plus I, which initially is 0, so you perfectly know by now that this is an expression that is used also as a boolean. I say, hey, do I have still something inside my string? Because I will increase highs, so I will reach at a certain point the end of the string, right? You perfectly know by now this. Then let's forget just by a second of this code. What do? Well, I print byte x, the function you perfectly know by now. This is a function that is able to print 1 byte in hexadecimal. I give as an input to this function what? The pointer str, which is a pointer to a char. I convert it to a pointer to byte, because the function takes 1 byte as an input. So I have a pointer to 1 byte plus I, that initially is 0. I dereference all of this, so I get the first byte of my string. This is gonna be the input of my print byte x, which is gonna perform its magic of putting in the standard output the hexadecimal of this byte, okay? And then I'm gonna increase I. Every time I'm gonna increase I until I stumble upon the last char, namely \0, that will behave as a false here. So it's gonna end my loop. Let's see the result of this function. I have the string that will be printed in its hexadecimal form, okay? Okay, I'm gonna run this code. You see, I have this series of hexadecimal numbers, which are 48, 65, C, okay? Let's watch. 48 is an H, 65 is an E, CC is an L. We have 2 of them, L, and then what do we have? 6F, which is O, hello. You see? Here there is written hello in hexadecimal, and of course you have all the string here in hexadecimal. till the last. Here we have 75. 75 is the U, of course, the last char of my string. You see, you have this one. That's perfect. You understand now how to print in hexadecimal a string. So basically the big part of this program is again this print byte in hexadecimal. Once you understand this point, it's done, my friend. This is the most important part indeed of this program, of the exercise in total, I guess. All right, last point. So here comes the last part of this very long video, which is you have to print the content in printable chars. If it's not printable, you have a dot. You see, here I declare a string, which is bonjour les amis, comment ça va? Inside this string, I have some non-printable chars. Then I have a variable, which is the size of this string. I can use size with an array, and I'm gonna get all the bytes of this data structure. And then I have an iterator I. The size is equal to the size of string, of course. It's gonna give me, as I told you, all the bytes occupied by this structure. And then I say size minus minus. Here I simply say, you know very well by now, if the char pointed by str plus I, which initially is 0, is minus 32 or is equal to 127, aka this string is going to be translated in is the char non-printable? Well, in that case, you print a point. Otherwise, you print the char pointed itself, okay? And then you just increase I. I think that's super easy. That's not, if you reach this exercise, you perfectly understand what is going on. So let's run this code. As you see, you have bonjour les amis with all the dots for the non-printable chars. Comment ça va aujourd'hui? That's it for the third piece of our long exercise. So here we are finally with the program itself, a big boy here. We understand very well to print the hexadecimal address, the content in hexadecimal, and the content in printable chars. We have the constraint that each line should handle 16 chars, and if size equals 0, nothing should be displayed, okay? Let's read line by line the code, and now we understand everything. So initially, I have my typedef unsigned char byte t. So I create my data type byte t. That by now you understand why. Here I have all my prototypes. Let's watch very briefly. I have a function that is going to print the address in hexadecimal, function that is going to print the content in hexadecimal, and the function that is going to print the content with the dot when there is an unprintable char. Okay. Then my top function byte in hexadecimal that is going to take 1 byte and write it in hexadecimal. Then I have ft print memory, which is the function of our exercise, and then a put char that you know very well. So let's watch our main. Here I have, it's very long, but because I do a lot of testing. Here I have an empty string. Here I have a random string, more than 16 char. Then I have all the strings of the exercise. And if I understand well, these strings should be longer than 16 chars, because here, up to here, you have 16 chars. Up to here, you have 16 chars. So I've padded with these lines to make them more real, to make them more than 16 chars, okay? Because here you have the constraint of 16 char. The only one which is not 16 is this one at the bottom, lol, lol, okay? So basically, I have all the strings of the exercise, and then I have my function, ft print memory, giving as an input a void pointer to the string. So I convert the string to the char to a generic void pointer. And the other input is the size. Given as with the size of operator, I can do that because this is an array. So it's going to be the total size of my array. So let's jump inside the ft print memory function. That's the one of the exercise. It's going to take a pointer, a void pointer, namely a generic pointer as an input, and then the size. They say when size equal to 0, nothing should be displayed. But an empty string has size 1 because we have the \0 char. So I think that when they say size, they imply the length of the string. So here, frankly, I don't know. I just assume that they say an empty string, so I say size is equal 1. So if size equal 1, just return the address. Don't do nothing. Here is up to you. Unfortunately, I don't have the moulinet, so I cannot test this part of the code. But this is not important. This is not the meat of this exercise. Then look how clean with my divide and conquer approach is the function. The first step, I'm going to print the address in hexadecimal, okay? Second step, I'm going to print the content of the address in hexadecimal, namely every char of the string. Third step, I'm going to print the content with a dot when I stumble upon an unprintable char. You see, this is all the ft print memory. I have an exit condition, and then I call 3 subroutines that are gonna help this function perform the task. You basically know all of them. Let's just watch very briefly. Print address in hexadecimal. First step. I have print address in hexadecimal is going to take a void pointer address, namely a generic pointer. Then I do my usual trick. I create a pointer to a byte, and pay super attention here, I assign the address of the address to this pointer to byte. Before, of course, I convert this pointer to a byte. So when I'm gonna dereference this pointer to byte, I'm gonna dereference 1 byte of the address, okay? This is the crucial part that you need to understand in all the exercise, in my opinion. Then here I declare a little endian variable, which is 7. You understand that in a little endian machine, we have the little byte in the little position. This is a trick to recall. So the most significant byte is in position 7. I need that byte initially. So I say while little endian is major equal than 0, I call my function byte in hexadecimal. So the function that is gonna print in hexadecimal 1 byte. I give as an input the byte pointed by the little endian address. So pointer to byte plus little endian, which initially is 7. I dereference this pointer. I get the byte which is in that position, namely the unsigned chart. You now understand pretty well. And then I just decrease the little endian. So every time I'm gonna take 1 byte, print in hexadecimal 1 byte, print in hexadecimal 1 byte, print in hexadecimal until I reach the byte number 0, which is the least significant one. I'm gonna print that, and then I have my address in hexadecimal. Then I'm gonna pad with this semicolon, which is the format that the exercise wants. Essentially, this function is gonna cover this part. It's gonna print the address with the semicolon. All right. The byte in hexadecimal function is this one that you know very well by now, I hope. With 2 implementation here, I left both. I have the one with the bitwise operation and the second implementation that is gonna use mathematics essentially. Okay, you understand how it works. Every time I call this function and I'm gonna print the address. Perfect. So then we're gonna print the content in hexadecimal of the string. So we have address and size as an input. So basically this output here is gonna be covered by the function. I'm gonna declare an I, an iterator, and then a limit. That limit is gonna be 16 because this is the constraint of the exercise. I restart as usual from 0, minus size, the size of the string, and limit minus minus. Of course, here I have the prefix minus because with the size I have even the \0 final. So I need size -1. Having a prefix is a trick to have immediately like size -1. You understand very well by now. And then I have the limit, which is 16. So this while loop can go on maximum 16 times. With these end limits, I set this constraint. Then look at this. I have to write the output with couples of 2 bytes, right? And then a space. So what do? I say if I modulo 2, we start from the beginning, which is 0. I modulo 2, what is 0, of course, right? 0 modulo 2 is 0. So 0 is false. If I invert this logic, I get through. So initially, I'm going to write in the standard output a space. On the following iteration, I get 1. 1 modulo 2, you get 1, so it's true. Invert the logic, false. I won't write the space. You see, so every time I get this toggle effect using the fact that the number is going to be even, odd, even, odd, even, odd, okay? I modulo 2 is simply a way of saying, hey, the number is even or not, okay? Easy. Then I invert the logic with this. So I'm going to print a space only when I is even, okay? That's the trick of these 2 lines. Then I call, as usual, my byte in hexadecimal. Here I have the pointers to a string that is converted to a pointer to a byte, and then I simply dereference all of this. I dereference all of this, so I get a byte that I can give to my byte in hexadecimal function that you know very well. Then I just simply increase str and increase I, okay? So at the following iteration, I have str plus 1, I have the following byte, and I keep going on until I have a size and I haven't crossed the limit. This is for padding reasons, you will understand by yourself, it's super easy. This doesn't need explanation. Okay, that's it for this part of the code. The function is gonna print this address. Okay, we have done. So we finish with the print content dot. As well, as usual, we give the address and the size. So now we have the final piece of this very long program. print content dot. Okay, so this is the function that is gonna handle this last part. Is gonna print all the string in this fashion with a dot when we have an unprintable char. That's super easy for you, I think, by now. I declare a limit. Limit is equal to 16. Basically, it is the same logic as before. I have a logical Boolean expression that is going to say while size with a prefix because I don't want the \0 final. So I need size -1 as before, and limit, so I don't cross the 16 limit. What do I do? Well, I say if str, I do a type cast because str initially is a void pointer, namely pointer without any type. I say, hey, dear str, now you're going to play the role of a pointer to char, namely a string. I dereference this pointer to char str, namely I get one char. And I say, if this char is major equal to 32 and this char is minor than 127, namely, is this char printable, is in the range of printable chars, well, then write the char, okay? Otherwise, what do? Well, you write a point because it is an unprintable char. And then you just keep going on. You increase with pointer arithmetic the string. You keep going on until this condition holds, and that's it. Okay, this is the function that is gonna print in the standard output all these strings. Okay, now we're gonna run the code and see how it works in its totality. You see, here I have the program itself. I have all the addresses, I have the contents of the strings, I have the constraint of 16 chars, and basically if you check, these outputs are the same of the output given by the exercise. Okay, we can also make the things that they require, like with the cat tier, and you see it's basically the same thing. Okay, so this is the output, everything works allegedly. Okay, now to make it super clear, I'm gonna uncomment the main with my addresses, so we're gonna check if everything is fine, at least with the first ones. Okay, so I run. See what we have. In the first case, I have only the main with the address, but my first string, let's see, is an empty string. So nothing, of course, gets printed. Perfect. Then we have this other string with this address, and as you can see, my hexadecimal address is the same. The string is this one, the string count. Then let's see, bonjour les amis. The string, this is the address from the main, this is the address from the return value, and this is the address in hexadecimal that I brought. This is hexadecimal of bonjour, 42, 6F, 42, 6F, 6E, 6A. All right, it seems like it works. Okay, my friend, that's it for this endless exercise. I will push it on GitHub so you can check by yourself, and I hope everything is correct, but just focus on the concept. It's not that important to pass exams, and in real life, if you understood the concept, the byte concept, like writing a single byte, the void pointer concept, and all the details of this exercise, in my opinion, you leveled up, okay? So thank you for watching, my friend. Enjoy.